Welcome students. In this video we are going to study a subject of independence. In the previous videos when we studied a subject on conditional probabilities, we were working with the cases when we modified our probability of event A given that some other related event B has already occurred. However, it is most often the case that an occurrence of some event has no effect on the probability of our event, let's say A. That is, probability of event A remains unchanged given the additional information that event B has already occurred. That is, conditional probability of A given B remains unchanged and is equal to probability of A. Events sharing this property here are known as an independent events. So let's take a look at the following definition. So two events A and B are said to be independent if probability of their intersection is equal to product of probability of A multiplied by probability of B. In fact, we can modify this definition and add a stronger statement if and only if statement. So two events A and B are said to be independent if and only if probability of their intersection is equal to the product of their individual probabilities. That is, if this statement holds true, then events A and B are independent. And if events A and B are independent, then that statement is going to hold true. So it works both ways. So this definition here follows directly from that property here. So if we define probability of A given B as probability of A intersection B over probability of B, and that should be equal to the probability of A, then we can derive that probability of their intersection is equal to the following product if events A and B are independent. Okay, great. Now let's take a look at a couple of examples. Let's start by proving the following useful property. If events A and B are independent, does it follow that A complement and B complement are also independent? Let's prove that. So we have to show that probability of A complement intersection with B complement is equal to the product of A complement by probability of B complement. Let's start off from the left side here and let's get to the right side over there. So we have probability of A complement intersection with B complement, which can be expressed as A union B complement using De Morgan's law, which is equal to 1 minus probability of A union B, which is equal to 1 minus probability of A plus probability of B minus probability of their intersection. Now, if events A and B are independent, then we can express this intersection as a product of probability of A multiplied by the product of probability of B. Okay, now let's open up the brackets here and group our terms in the following way. 1 minus probability of A. Then we have minus probability of B. This 2 gives us plus, and we are factoring out minus again. So this will end up with minus probability of A multiplied by probability of B. So we have 1 minus probability of A minus probability of B, 1 minus probability of A. Now let's factor out 1 minus probability of A here. So we'll have 1 minus probability of A multiplied by 1 minus probability of B. These two are defined as probabilities of A complement and probability of B complement. So we have probability of A complement multiplied by probability of B complement. Thus we have proven this statement here. If two events A and B are independent, then their complements are also independent. Let's take a look at one more example. So we have a company, so they are hiring people now. So far they hired 120 people given in the following table here. Now they want the following two events to be independent. Let's call event A. Event A of being a black, and event B being a woman employee. So our company directors want the following two events to be independent. And now let's calculate how many black females we should hire. For events A and B to be independent, probability of their intersections should be equal to the probability of A multiplied by probability of B. Okay, now probability of their intersection is event of their intersection is an exactly event of being a black female employee. So this number is given as X over the total number of workers in our table here, which is equal to X over 120 plus X. Now that should be equal to probability of A, probability of being a black woman, probability of being a black worker. So black, the number of black employees is 30 plus X over the total number of employees, which is 120 plus X, multiplied by probability of being a woman employee, which is given as 40 plus X over 120 plus X. Now solving this equation gives us exactly 24. So we should hire 24 black females for these two events to be independent. Now, sometimes we can derive independence of two events based on the physical conditions surrounding our events. For instance, it seems to be obvious that two events, an outcome of your coin toss and the color of t-shirt you wore last Friday, have no connection whatsoever, and occurrence of one event has absolutely no effect on occurrence of the other. Or let's say if you are tossing a coin twice in a row, and it seems that an outcome of your first toss has no effect on the outcome of the second toss. In those cases, in cases when we can derive independence of two events based on some physical conditions, then we can apply our theorem of independence of two events. That is, we can directly use that intersection of two events A and B is going to be equal to the product of their individual probabilities. Let's take a look at the following example. So we have summer interns. They work as proofreaders. Myra and Carlos. Myra has 50 chance of spotting an error. So probability that Myra is going to spot an error is 0.5. Carlos picks up on the same kind of mistake 80% of the time. Probability that Carlos catches an error is 80%, 0.8. Suppose the copy they are proofing contains an error. What is the probability it goes undetected? So we are looking for probabilities that error will go undetected. That is, we are looking for probability that both Myra and Carlos will fail to detect that error. That is, we are looking for probability of intersection of M complement with C complement. Okay, which is equal to 1 minus probability of M union C. This is by De Morgan's law. M union C complement, and that is equal to 1 minus probability of their union, which is then equal to 1 minus probability of M plus probability of C minus probability of their intersection. Okay, now let's assume that Myra and Carlos are working independently. Let's assume that they work independently is given in the conditions of our problem. Then we can apply an independence here and express this probability of intersection as a probability of product of individual probabilities. So that can be expressed as a probability of M multiplied by probability of C. So we have 1 minus probability of M minus probability of C plus probability of M multiplied by probability of C. Right now we know probability of M, we know probability of Carlos, probability of M, and probability of Carlos. Okay, now let's take a look at one more example. Emma and Jones have just gotten engaged. What is the probability that they have different blood types? Blood types for general population are distributed as follows in the following table. So we are looking for probabilities that they have different blood types. Now finding probabilities that they have same blood type will be easier since there are less possibilities in the case when they have same blood types. So let's work with the complement of that. So this is 1 minus probability that they have same blood types. Now Emma and Josh will have the same blood type in the union of the following events. In the case when both Emma and Josh are of blood type A. So Emma is blood type A and Josh is blood type A. Or both of them are blood type B. Or both of them are blood type of AB. Or both of them are of blood type O. Now, let's take a look at these events inside of the brackets here. All of these are mutually exclusive since, for instance, the following two events cannot happen at the same time. Both Emma and Josh have blood type A, cannot occur at the same time with the following event. Both Emma and Josh have blood type B, so they either have both blood type A or either have blood type B. Cannot happen at the same time. So we can express the probability of union of these events as a sum. And so on. Now, let's assume that it was given in the conditions of our problem that Emma and Josh did not choose each other as partners based on their blood type. So we'll assume that the events of them having a specific type of blood type, these are independent. That is, we can express the probabilities of these intersections as the probabilities, as a product of individual probabilities. And so on. So this is 1 minus probability of Emma having blood type A is 0.4. Josh having blood type A is also 0.4. Blood type B is 0.1, so it's 0.1 squared, plus blood type AB is 0.05 squared, plus blood type O is 0.45 squared.